Now that we've gone over the methods to appropriately analyze a beam, as well as applying those methods to 3-point bending, let's take a look at how they actually apply to 4-point bending as well. 4-point bending tests are commonly used to assess the mechanical properties of brittle materials, just like in 3-point bending. However, they offer certain advantages over the use of 3-point bending tests. 4-point bending tests are usually conducted on rectangular beams. These beams are placed on 2 roller supports, and then load is applied via a 3rd and 4th roller. These are usually mounted symmetrically about the middle of the loading span. The specific dimensions can change, however, ASTM E855-08 specifies that the supports are located 1/6 of the total length from the outer supports. As a result of this bending, a normal tensile stress is developed in material on the convex side of the beam, while compressive stress is generated on the concave side of the beam. And as a reminder, both of these are normal stresses. The first step in analyzing this test method is to convert our setup to its free body diagram. As we are symmetric about the midsection, I've replaced each roller with an applied load of F/2. By now you should be able to easily solve for these support reactions by placing the beam in static equilibrium. Once the free body diagram is in place, we can then begin to analyze the 3 unique regions on this beam, regions AB, BC, and CD. In region AB, I will place an imaginary cut, a distance x from point A. On the face of this cut, a moment and a shear force will be required to ensure that the beam remains in static equilibrium. Once again, note that I have drawn the shear force and moment in the positive direction according to our previous sign convention. Once we have identified the potential internal loads, we can use the equations of static equilibrium to determine their magnitudes and directions. In this case, we see that in region AB, there is a constant shear force of magnitude F/2. Also in region AB, there is a moment that varies linearly from 0 at point A to 1/12 FL at point B. Up next, we can carry out this exact same analysis, but this time on region BC. In this region, we see that the applied loads actually cancel out, and because of that, we have 0 shear force present within this region. Because we have 0 shear force in this region, we are left with a constant moment that equals 1/12 FL. However, remember that the magnitude of this moment is dependent on the spacing of the applied loads. Finally, we can carry out the same analysis, but this time in region CD. In this region, we see that there is once again a constant shear force, however this time its value is negative F/2. And furthermore, we now have a moment that once again varies linearly, but decreases to 0 when x is equal to L. An easy way to summarize these results is to present them in the form of shear and moment diagrams. In the shear diagram, you will see that we have 2 regions where we have a shear force that is 1/2 F, either positive or negative, and a central region where we have 0 shear force. In the moment diagram, you will see a plateau where between regions B and C, the moment is a constant magnitude, and due to the initial spacing of these applied loads, in this case the maximum moment is 1/12 FL. Using the bending stress equation and the knowledge that the x-axis runs through the centroid of the cross-section, we know that the maximum stress occurs at the top and bottom surface of this beam. We can calculate this stress by inserting the value of the maximum moment, FL/12, the distance from the neutral axis, plus or minus h/2, and the area moment of inertia about the z-axis, 1/12 bh³. This equation can further be simplified into a more usable form. As mentioned in the 3-point bending video, one way this stress can be experimentally determined is to mount strain gauges to the upper and lower surfaces of this beam. Then we can use Hooke's law to relate the recorded surface strain to the applied load and specimen properties. This setup is almost as easy to put together as 3-point bending and offers the advantages of generating a larger region of uniform bending stress. The slight drawback to 4-point bending is that it should be carried out by measuring the deflection of the beam's midsection. This requires a slightly more complicated setup to measure the deflection. However, as it's not very difficult, the rewards are definitely well worth it. Don't forget to post any questions you have, and we can make sure to work through them together.